Hi everyone. Today I will going to explain d-orbital splitting pattern in regular octahedral complexes. So by the title you may have some confusion. What is the regular octahedral? Is there any different types of octahedral structure? Yeah, there will be. We can quote that there will be two different octahedral structure. One will be called as regular octahedral. Other will be called as distorted octahedral. So what would be the differences here between regular octahedral and distorted octahedral is the bond lengths of metal to ligand. If the all six bonds in octahedral metal complex are equal to one to other, then it will be called as regular octahedral. If the bond lengths are different, if the bond lengths are different, then thus the octahedral will be called as distorted octahedral. So by next you will come to know which type of complexes will have example complexes you will going to have in distorted octahedral. We will give you certain examples, and we will also have the splitting pattern, d-orbital splitting pattern in distorted octahedral also. There we will give you exact example. I will give you example, and with respect of that I will explain you the splitting pattern also. By here you consider that general octahedral, till now what you know, that general octahedral where metal to ligand bond is equal for all the six bonds, right? So here we know that the complex, right, octahedral, it examples as ml6. ml6 metal 6 coordinated ligand complex will be known as octahedral complex, right? So this octahedral complex is not an two-dimensional complex. Even we are projecting on one paper, all the six ligands are approaching towards the metal ion on same plane. It is not like that. It would be different, right? So previously, as I explained you, the ligand approach, while we are defining the d orbital splitting pattern, we have to be know exact how ligand approaches towards the metal atom, and the d orbital shapes, structures or shapes, right? Previously we all discussed that the d orbital shape, how they are, how the 5 d orbital loops are arranged. So for each structure, right, from now onwards we have to know that for each complex structure, how the ligands exactly arranged, how the ligands are exactly approaching towards the metal atom. This is, we have to be very cautious, right? To define this, right, we have to incorporate this particular complex structure into three coordination axes, right? We know that there are three coordination axes such as x, y, z, right? So same, if we are incorporating this x, y, z coordination axis on this particular octahedral structure, the origin point will be exactly middle, right? It would be on metal atom, right? And here when we are pointing z orbital, the z orbital will be like this, up to down, right? Up to down, the z axis will be there, right? And the left to right, the left to right x axis we can project, and the front to back we will going to express the y coordination axis, right? The left to right x coordination axis, front to back y coordination axis, top to down z coordination axis, right? So if we are arranging this octahedral structure here, right, before this class, same the arrangement I taken to express the all three coordination axes. Consider this particular left and right axis as an x-axis I considered, and this particular front to back, and back front and back sorry front and back, this particular will be y-axis I consider, and the top and down, right, top and down I consider as z-axis, right. So z, y and x, right. So here, if we are keeping all octahedral structure, if we are imagining octahedral structure, right, ml6 complex, the middle origin what I taken, this will be have metal ion here in the point of this, the metal ion will be there, and towards x-axis, right, left side one ligand, and for the right side here there will be another ligand. On z-axis, front and back, and back side there is one ligand, on front side there is another ligand, right. On z-axis, right, top and down, at the down position there will be one ligand, on the top will be another ligand, right. Like this, all six ligands will be arranged in an octahedral like this, right. So octahedral is an six coordinated complex. Octahedral complex is six coordinated complex. Six coordinated complex where each coordination axis will have two ligands. Along each coordination axis there will be two ligands like this, right. On x-axis 2, on y-axis 2, on z-axis another 2, all 6, right. So this is how the ligand arrangements will be there, right. So the d orbitals which are now we can say that now here we will conclude that all six ligands in octahedral complex are along the coordination axis, right. That means each ligand, so each coordination axis, when there are two ligands out there, nothing but all the ligands on coordination axis, right. So by which we can say that the d orbitals lobes which has which have along the coordination axis will get repulsive interaction and get excited to higher energy level, right. So that is the things we can conclude, isn't it, right. As per the structural aspects of octahedral, all six ligands are along the coordination axis on all three coordination axes. So far, if the metal d orbitals which are having the lobes along the coordination axis, what happens? They get repulsive interaction. They will get interacted with these ligands, right. So there the repulsive interaction, negative interaction, it takes place. So far, thus orbitals will get unstabilized, destabilizes, and reaches to higher energy level, excites and reaches to higher energy level, right? Isn't it? So now look into each orbital of d orbitals, right? So we know that the d orbitals are 5, 2, 3, 4, 5, right? The d orbitals. So initially what happens is that uh, free metal ion, when this free metal ion get interacted with the 6 ligands, initially get excites, all 5 orbitals initially get excites, after which they going to have splitting. Some will get into excited, some will get into lower their energy. Which we are going to be excite, which of the orbital, which of these 5 d orbitals get into low energy level, we have to look it, right? Initially going with an dxy orbital, right? Dxy orbital, how it would be the have the lobes, how it has the lobes, right? Consider same, this is what x-axis we consider, this is at y-axis we consider, right? The dxy orbital lobes, how they are in between the coordination axis, here 1, here 2, here 3, and here 4th, right? All the lobes are in between the coordination axis. How far the ligands? They are either along the x-axis or along the y-axis or along the z-axis. So the ligand are passing through the coordination axis, but the lobe of dxy exactly in between of the coordination axis. So far there will be no interaction between this particular middle orbital lobe with the ligand approach, neither x-axis ligand or neither y-axis ligand or not with the z-axis ligand. There is no interaction with these ligands with the dxy lobe, which is in between the xy coordination axis. So far, once there is no interaction of dxy lobes with the all 6 ligands, it get stabilizes and it reaches to the lower energy level, it reaches to the lower energy level, right? Same if we are going with dyz, and we know that the dyz also, right, has the lobes in between the coordination axis. If this is the z and this is the y, right? So the lobe will be in between the coordination axis, not along the x axis or y axis, not along the z axis, right? It will be in between the xz axis, right? So where the ligands again they are along the coordination axis, they never be towards the this particular middle lobe, right? It never have any interaction with this particular dz dyz orbital, which is having the middle, which has the lobes in between the coordination axis, right? There may not be z ligands will approach, there may not be the y ligand can approach, right? So again, the dyz, which having the lobes in between the coordination axis, never have any repulsive interaction, never participate with any repulsive interaction with ligands. So again it can again stabilizes, reaches to lower energy level. Same if you are going with zx, dzx orbital, this also has the lobes in between the coordination axis, and it can never be have any, it can never be participated any repulsive interaction with all the 6 ligands, right? And this is x, this is z, right? Zx, so the lobe will be here, right, in between the z and x. So here will be the lobe, right? It can never have any interaction with either z ligand, z axis oriented ligand, or y axis oriented ligand, or it is so far away from the even with the uh, y-axis ligands, right? Either it cannot be interact with the z-axis oriented ligands, x-axis oriented ligands, and it never be have any interaction with y-oriented ligands, right? So the dzx lobe, which is have in between the coordination axis of x and z, so it never have any repulsive interaction, so it get again stabilizes, right? It will also stabilizes, reaches to the lower energy level, right? And thus lower energy it equal with the dxy dyz. All these three will get into lower energy state. Now coming to dx square minus y square. Consider the orbital of dx square minus y square. How far the lobes of dx square minus y square? Right. This is what the x-axis. This is what the y-axis. This is y-axis. This is x-axis. Where the dx square minus y square has the lobes along the x-axis, two lobes, and along the y-axis there is another two lobes. Right. So here the dx square and minus y square has along the x-axis two lobes, along the y-axis two lobes, which are towards the x-axis ligands and towards the y-axis ligands. It may be far away from the z-axis oriented ligands, but they are very nearer. They are very nearer, closer towards the x-axis oriented ligands and y-axis oriented ligands. So far, what happens? They get participate in repulsive interaction. The lobes, how they are? Along the x-axis too, along the y-axis too. So what happens? These lobes, x-axis oriented lobes, will get repulsive interaction with x-axis ligands, and y-axis oriented lobes will be has participate in the repulsive interaction with y-oriented ligands. All these four ligands will get full repulsive interaction with dx square minus y square, gets repulsive interaction. So far, thus the dx square minus y square gets exact its energy, right? To stabilize, to overcome such repulsions, the dx square minus y square enhances its energy, reaches to higher energy level, and destabilizes. To get stabilized, it enhances its energy. Coming to dz square orbital, same, the dz square orbital, how they are? Along the z axis two lobes, and at the middle, all along all the three coordinate axes, another spherical. So which means of that, the z oriented two ligands will have direct repulsive interaction with the dx square minus y square lobes, and the all four ligands which are along the x axis and y axis, right, will have partial interaction with the spherical lobe of the dx square minus y square. So in which, right, the dx square minus y square also have repulsive interaction, will participate with repulsive interaction with these all six ligands of octahedral. Then by which what happens? To overcome such repulsive interaction, the dz square also will get excites, and the excited level will reaches to the dx square minus y square energy. So far, these two orbitals in octahedral complex, these two orbitals dx square minus y square and dz square will gets excited, reaches to the higher energy level, and the three orbitals which are dxy, yz, zx, they will reaches to lower energy level, right, reaches to same energy. This will be called as triply degenerated level. Triply degenerated level. Triply degenerated level represented with T2G, and the excited energy level will be called as doubly degenerated level. Will represented with EG. Will represented with EG. right? So that's how the octahedral splitting pattern can takes place in uh, octahedral complexes. D-orbital splitting takes place in regular octahedral complexes, right? Here, to have the statements, if we observe properly, these three orbitals which are getting lower energy, right, they are non-axial orbital. So far we can make a statement that the non-axial orbitals dxy, dyz and dzx will stabilizes where no interaction with ligands gets lower energy state, lower energy state, that is T2G, triply degenerated state. Triply degenerated state. Okay. Triply degenerated state. Statement number 2 is the axial orbitals dx square minus y square and dz square will have repulsive interaction with ligands and get excited into higher energy level. That is doubly degenerated EG level, EG state or EG level, right? So this is how the d orbital splitting pattern in the regular octahedral transitional metal complexes, right? Here I conclude the today's subject. By next we will going to discuss another structural d orbital splitting pattern. Okay, right.